I would like to do a couple of examples involving finding instantaneous rates of change or slopes of tangent lines by using some different functions. In this first example, we'll deal with the function 1 over x squared and find the instantaneous rate of change at an arbitrary point x0. So we'll start with the interval starting at x0 and ending at x0 plus h. And of course, we'll take the limit as h goes to 0 or as the right endpoint becomes the left endpoint of this interval, all right, to find the instantaneous rate of change. So let's see, what will we have here? Okay, well, we'll start with the left end, x is equal to x0. Then f of x is going to be 1 over x0 squared. All right, at the right end, the x value will be x0 plus h, and the y value, or the function value, will be 1 over the quantity x0 plus h squared. The change in x will now be x0 plus h minus x0, or simply h, and the change in y will be 1 over the quantity x0 plus h squared minus 1 over x0 squared. So the average rate of change in y with respect to x over the interval from x0 to x0 plus h is going to be the change in y, 1 over x0 plus h, the quantity squared, minus 1 over x0 squared, all divided by h. Now remember, what we want to do is take the limit as the right endpoint becomes the left endpoint, so as x0 plus h becomes x0, or as h goes to 0. So then the slope of the tangent, oops, sorry about that, the slope of the tangent is going to be the limit as h approaches 0 of 1 over the quantity x0 plus h squared minus 1 over x0 squared, all divided by h. Okay, in the numerator, we'll get a common denominator. We'll multiply the first fraction by x0 squared over itself, and the second by x0 plus h squared all over itself. Okay. Remember, we're also dividing by h, which is the same as h over 1, so I can, instead of dividing by h over 1, I can multiply by its reciprocal, and so I'll do that at the same time. We're going to have now then the limit as h approaches 0 of, in the numerator, I'll have an x0 squared minus an x0 plus h squared, all over x0 squared times x0 plus h squared times, instead of dividing by h over 1, times 1 over h. Okay. All right, let's expand and simplify the numerator here. I won't bother multiplying out the denominator, so we'll have an x0 squared minus, when I expand this, be careful that you don't forget to distribute the minus sign through this entire expression. We'll have x0 squared plus 2 x0h plus h squared. And remember, we have to subtract all of that, all right? And this will be divided by x0 squared times the quantity x0 plus h squared, and times the h. Okay, distributing the minus sign through to each term, this will become the limit as h approaches 0 of x0 squared minus x0 squared minus 2 x0h minus h squared all over x0 squared times the quantity x0 squared, x0 plus h squared, excuse me, times h. Notice, of course, the x0s subtract, x0 squared subtract off, all right, and we're left with a negative 2x0h minus h squared, which each term has a common factor of h, so we can factor the h out, and we'll be left with h times negative 2x0 minus h all over x0 squared times x0 plus h squared times h. The h's cancel, and I underestimated the room that I would need here, so let me insert a page. Okay, oops, I may have done this in the wrong place. I think I needed to append a page. I'm making lots of mistakes here. All right, and so what's left here is the limit as h approaches 0 of negative 2x0 minus h over x0 squared times x0 plus h, the quantity squared. Now, provided x0 is not 0, all right, and we would have real problems if x0 was 0, because the function itself would have been undefined. This would have been undefined at the left endpoint, so we couldn't let that be the case. So for x0 not 0, this would become simply negative 2x0 minus 0 over x0 squared times x0 plus 0 squared, all right, and that would be negative 2x0 over x0 squared times x0 squared is x0 to the 4th. Simplifying, we'd have negative 2 over x0 to the 3rd. Negative 2 over x0 to the 3rd. Let's take a look at an example of this. So the slope of the tangent line, all right, is going to be given by negative 2 over x0 cubed. Okay? And let's take a look at what we have. Let's look at this, all right? Again, we have this situation. I'm using 1/2 for x0, all right? But we could use different values. All right? There's my secant line. Notice in this case, we're going from 1/2 to 1.5, so h is 1. H is this horizontal distance from the left end of the interval to the right end of the interval. And then as we reduce the size of it, all right, notice, all right, this slope at this point is getting closer and closer to 16, and if we let h go to 0, it actually does become, I should say, negative 16. All right, and that would make sense because, let me minimize this for just a moment. All right, because when x0 is 16, or is equal to 1/2, all right, then that tells me that x0 to the 3rd is 1/8, and 1 I should say negative 2 over x0 to the third is negative 2 over 1/8, or negative 2 times 8, which is negative 16. All right. But now, all right, what we can do is we could change the value of x0. All right, if this was at 1. Let's make x0 1. Okay. Oops, I went a little too far. Okay. Now when x0 is 1, all right, notice that the slope here is negative 2. All right. And again, if we would put 1 into this formula, negative 2 over 1 cubed would be negative 2. We have actually now a formula for the slope of the tangent line.